So as everybody could see, there's been a lot of work going into the conceptual design, but there's also been a lot of work on getting data together to test the model and to fit all of those various relationships that Hamish and Enley have described. In parallel to that, we've been setting up a system because you'd understand that that's a significant change to the phenology model, and that phenology is important to the way in which our model predicts even other processes, including canopy development and grain yield. So if we, for example, have improved our predictions of final leaf number, that will change our predictions of flag leaf date and canopy size and all of that. And so to approach that, we've made sure that we've gotten as much test data into the system as we could before we implemented the change into the phenology model. So as a result, the test set in the APSIM wheat model has grown to, I think, something like 6,500 crops. Inside that, that's all of the data as part of this project that Enley described. But we have a lot of legacy test data sets in APSIM as well that goes back to, even, well, early in the last century. So we've also chased extra field data for important varieties like Hartog or some of the other varieties that we used in historical data sets, including some of the face data, so that we had better, so that we could actually fit some of these parameters with more confidence so that we could test the historical data sets. So to do that, we've also had to estimate the parameters. So Hamish and Bang Yu and Emily have worked to fit many of these parameters from the test data sets that we've had in this project. We've also had to estimate, using the best approaches we could find, parameters for the historical data sets. We then put that all into version control so that all of that data is available and was running on the previous version of the wheat model. So that now, when we put the new phenology model in, and there's a pull request currently on GitHub that people can look at to see, and I'm sharing that screen right now, you can see the effect of the new phenology model on that whole test data set versus the old phenology model on that whole test data set. So what we can see here is if we work sort of mechanistically through the way the model works, Hamish has just described how the model works, we can see, for example, we now have 857 records for final leaf number, and the model, the new phenology model is the first number here. That is compared to the old phenology model. And we can see there are ticks for all of these phenological predictions here. So we have improved the model predictions with using the new model. So if we just look at some of these, for example, if we look at final leaf number, the red is the new model, and we can see we've collapsed a lot of the error in the predictions final leaf number across 857 wheat crops. And I can show you similar data with that's final leaf number that flows through into predictions of the flag leaf date. We can see we're using the data that we've got, we do a lot better than the estimates that we had previously. Then if we look at our heading, if we work in chronological order, we've about approximately halved the error in the prediction of heading date across about 5,000 crops for which we have heading date. And then finally, if we look at flowering date again. So pulling that new model with the parameters that we've developed helps across not just our data sets from this project, but the historical stuff as well. As I said, you change anything in the model that changes the outcomes. And so there were impacts of improving the phenology model on our estimates of other parts of the model. So what we have here, we can see, for example, that by improving the phenology, that did have impacts on other predictions. And they are the ones here that have the red crosses. So in terms of our predictions of grain weight, there is a slight change in the predictions of grain weight. And if I look at that, for example, what we find is that in most of the data sets, there are just minor changes from changing the timing of phenological data, improving those predictions. That does have small impacts on our predictions of yield. In this case here, the most impacted ones are some of these high yielding crops in New Zealand, which, you know, Hamish, if you have questions, Hamish can explain some of the issues there. But we've had to go back through a lot of the old test data sets, and yes, there are small errors or increased errors in some of the crops, but they will require a lot of work to go through and understand, well, what, now that we've got phenology right, what else do we need to deal with in some of those trials? And some more work will have to happen there. In some cases, we only have information for one crop for a given cultivar. In those cases, we have assumed, well, where we've got data, we can use that to help estimate parameters for phyllocrines or the like. If we only have one planting date, we know nothing really about some of the responses. And in those cases, we have tried to find parameters that seemed plausible and reproduce the old models' phenology predictions. That was the best that we could do in the absence of any other information. So there's would be perhaps further work to go with testing down the track, but across these, what we're finding is things such as, we can sort of go back and look at the above ground biomass. For the majority of crops, there's a very minor impact on the predictions from improving the phenology observations, apart from some of these high yielding crops at the top end there. As I said, this is all on GitHub, and we can answer further questions later if people are interested in understanding the impact of the new phenology model on model behaviour.